Happy day. Today's session is on conformal mapping and the elementary transformation. So, we all know what you mean by a mapping. The mapping is the activity or the process to represent something. In the context of mathematics, the mapping is the synonym of mathematical functions and the generalization. Here, now we are going to see about the conformal mapping. So, what do you mean by a conformal mapping? Let f be an analytic function in a region D. Let C be the curve given by z equal to z of t, where a less than or equal to t less than or equal to b are lying in D. So, this is the definition of the image of the curve, right. So, before seeing the conformal mapping, we will discuss about what is the definition of the image of the curve. So, you have the two planes similar to real axis, real number system. In the complex system, we have the two planes. So, one is the z plane, another is a w plane. The z plane, usually it is represented by a complex number z naught or any number in form of a z which is equal to x plus iy. Similarly, the w plane is the image of this curve or the z which is w equal to u plus iv. So, here the equation w of t equal to f of z of t defines another curve c prime in the w plane and is called the image of the curve under f. Now, we will see the definition of a conformal mapping. Let f be a continuous function defined in the regular in the region D. Let z naught belongs to D. So, we have a point z naught in the region D. Then we are going to define a two curve C1 and C2. We get two regular curve. What do you mean by a regular curve? The regular curve is nothing but the derivative is not equal to 0 at the point z naught. C1 and C2 are intersecting at the z naught which is x naught comma y naught in the w plane. So, now we will see the definition of a conformal mapping. Let f be a continuous function defined in the region D. Let z naught belongs to D. Let C1 and C2 be the regular curve passing through the z naught lying in D. Let C1 prime and C2 prime be the two curves in the image of C1 and C2 under F. If the angle between C1 and C2 is equal to the angle between C1 prime and C2 prime both in magnitude and direction, then we say F is conformal at Z naught. Thus, a conformal mapping preserves both in magnitude and the direction that is represented in the diagram. So, what we have defined we have represented through a diagram. Similarly, next definition is the isogonal mapping. The definition holds good, but the magnitude, the angle between C1 and C2 is equal to angle between C1 prime and C2 prime. Its magnitude is equal but reverse in direction. Then we say the F is a isogonal mapping at Z naught. So, this is a representation of isogonal mapping. We can see the angle is the same in the both the plane, but the directions are reversed. Now comes the scale factor on the angle of rotation. Now we see the scale factor, that is the image and pre-image. So, this is the original picture that is transformed through some transformation through a function. We get the image of the triangle. It can be through a angle of rotation, it can be through a 90 degree or 180 degree the angle of rotation. So, that is represented, that is called as a scale factor and the angle of rotation. So, we take a problem to define what you mean by the scale factor and the angle of rotation. Here we are going to determine the angle of rotation and scale factor at the point z equal to 1 plus I under the mapping z square. So, we know that what do you mean by scale factor? The scale factor is defined as the modulus of f dash of z naught. So, and our angle of rotation is defined as the argument of w dash of 1 plus I. Here 1 plus I is the point, right, and the scale factor is modulus of w dash of 1 plus I. Now, we are taking the function w equal to z square, the differentiation we all know what is the differentiation of z square with respect to z, which is nothing but 2z. So, at the point z naught we are defining, that is w dash of 1 plus I, that is 2 into 1 plus I, which is tan inverse. The argument of 2 into 1 plus I is nothing but the tan inverse of 1, which is pi by 4. The scale factor at z equal to 1 plus I is given by 2 root 2, that is modulus of f dash of z naught modulus of w dash of 1 plus I, that is 2 root 2. Now, similarly another problem, we are going to find the points where the mappings are conformal and the critical point. So, already we have defined what is a conformal. The conformal mapping, the derivative is not equal to 0 at the point z naught. Here, so w equal to z power n, we know that what is a conformal mapping at z naught, this f of z is analytic and f dash of z naught is not equal to 0. But what is the critical point? Critical point is z naught is a critical point of w equal to f of z if f of z is analytic and f dash of z naught is equal to 0. So, w equal to z power n, we are finding f dash of z, this is n into z power n minus 1. When it is 0, f dash of z is equal to 0 if and only if z equal to 0. Hence, the mapping is conformal at all the points except z equal to 0. So, what is the critical point here? Z equal to 0. Now, we come to the elementary transformations. So, these types of transformation we are seeing in the day to day life, that is in the, you are using the mobile phone, the swiping, zooming, all this activities are done due, by applying the by the application of the elementary transformation. Now, the first one we are going to see is the translation, the w equal to z plus b. Now, as usual, w, what is a w? W is here equal to z plus b. So, we assume z equal to x plus iy, w equal to u plus ib, and similarly b is nothing but as imaginary number b1 plus ib2. So, then the image of the point on the xy in the z plane is represented by in the x plus b1, y plus b2 in the w plane. Under this transformation, image of any region is simply a translation. That is, what do you mean by translation? It has the same shape, size and the orientation. So, suppose in particularly, if you want to take the image of a straight line, the image of a straight line is a straight line, and the image of a circle with a center A and radius is a circle with center A plus B and the radius R. So, what are the fixed point here? The fixed point here is the infinity when b not equal to 0. Next we comes the rotation. So, rotation is nothing but w equal to a z where modulus of a equal to 1. So, we assume that we are going to define z as in polar form r equal to e power I theta, a equal to e power I alpha with modulus of a equal to 1. So, w equal to a z, after substituting we know e power I alpha into r e power I theta. After simplification we will get r into e power I theta plus alpha. A point with this polar coordinates. So, we have expressed in the polar form, the coordinates also in the polar. So, r comma theta is nothing but in the z plane which is mapped to the w plane. So, what happened in the w plane? R remains the same, but theta is nothing but theta plus alpha. So, here comes the rotation. So, the rotation angle alpha is nothing but the argument of a about the origin. So, in this transformation also the straight lines are mapped into the straight lines and circles are mapped into the circles. So, 0 and infinity are the two fixed points. Now comes the magnification or the contraction. We have seen this symbol in the zoom, right, in the web pages or in any other Word document or PDF, the plus and minus sign denotes the zoom in and zoom out. So, that is nothing but the magnification and the contraction. So, here the transformation is defined as w equal to b z. B is a real number and b is greater than 0. So, it is not the less than 0, since it is a real, we have taken b is greater than 0. Here also we taken the polar coordinates r comma theta in the z plane and is mapped on to the. So, what happened in the w plane? It is a point becomes br comma theta in the w plane. Since this transformation, it can be a magnification or it can be a contraction, it depends on the b. If b is greater than 1, then we get a magnification, and b is less than 1 becomes a contraction. So, here the transformation is also, here also the transformation of the straight lines are mapped into the straight lines and circles are mapped into the circles. So, in general the rotation of the angle argument b, right, followed by the magnification together, we call this transformation as homothetic transformation. Now, the important transformation is the inversion, that is the inverse transformation. You have taken w equal to 1 by z. So, w equal to 1 by z in polar form we are expressing as w equal to 1 by r into e power minus I theta. So, because 1 by z, what is z? Z equal to r e power I theta. So, when you take to the denominator, it becomes a negative e power minus I theta. So, this transformation can be written as the two transformation, product of two transformation. So, one transformation I can take it as T1 of z 1 by r e power I theta, another one as r into e power minus I theta. If we take the product of these two, we will get the z bar. So, z bar. So, T1 of T2, that is the composition of the two transformation, we will get 1 by r e power minus I theta. Now, this represent the unit circle, the modulus of z equal to 1, and T2 of z represent the z bar, which is a reflection about the real axis that you have represented in the figure. But the before transformation, the previous transformations and all, we have seen straight line is mapped into the straight line, circles are mapped into the circles. But in the inversion transformation, here the point outside the unit circle are mapped in the inside the unit circle of the W plane. So, then points on the circle are reflected about the real axis. So, that is denoted here. You can see the points in the Z plane, that is a Z plane. So, in the Z plane, the points outside the circle is mapped onto the 1 by z. So, where it is mapped? It is mapped onto the 1 by z inside the circle. Now, what about the Cartesian coordinates? So, how the transformations are in the Cartesian coordinates? So, W is usually we represent the point in the W plane will be u plus iv. So, u plus iv equal to 1 by x plus iy. So, by the conjugate, so u will be x by x square plus y square and v equal to minus y by x square plus y square. Now, we are going to take an example under the inverse transformation. So, under the transformation of W equal to Iz plus I, show that the half plane x trans greater than 0 maps onto the plane W greater than 1. So, these are the two planes, one is the Z plane, other one is the W plane. So, we have seen the image. By seeing the image, we can see the point that is x greater than 0, that is a real part. So, that side of the x, which is a positive side, positive quadrant, that is mapped onto the v greater than 1. This is represented, the diagram represents the question, is understood from that diagram. So, how you prove this? So, by prove this, we will take z equal to x plus iy, w equal to u plus iv, and w equal to, here the transformation is Iz plus I. So, we substitute what is z, z is x plus iy plus I, and separating the real and imaginary part, we take u equal to minus y and v equal to x plus 1. Now, they ask us to prove only x greater than 0 and we have to prove only v greater than 1. So, we are not bothered about the u, we bother only about the v. So, v is greater than 1. So, if v is greater than 1 implies what? So, v is greater than 1. So, implies what? If you substitute 2, what will be the x value? X will be definitely greater than 0. Similarly, x greater than 0, we substitute x equal to 1. So, v is greater than 1, v equal to 2. So, that we have seen we have seen the diagram. Next problem, this is by means of the inversion mapping W equal to the inversion mapping W equal to 1 by z, the circle given by modulus of z minus 3 equal to 5 is mapped onto the circle modulus of W plus 3 by 16 equal to 5 by 16. So, we are going to by the means of inversion, right. So, the circle is modulus of z minus 3 is mapped onto. So, we are going to substitute what is the inversion. So, it will be 1 by w minus 3. So, I will substitute what is w u plus iv. So, taking after simplification, we have get the circle equation. So, u square plus v square plus 6 by 16 of u minus 1 by 16 equal to 0. Right. So, here the center is nothing but we all know what is the center of the circle, minus g comma f, that is minus u comma minus v, right. So, 2u we compare 2u equal to 6 by 16. So, if you simplification we will get minus 3 by 16, v is not there. So, we are taken as 0. So, radius you know, the formula of the radius we get 5 by 16. Now, what is the application of this conformal mapping and the elementary transformation? The application of this is a Mercator projection. So, what is a Mercator projection? So, Mercator projection is nothing but a conformal cylindrical map projection. So, that was created to display the accurate compass bearing for sea travel. Right? So, all the local shapes are accurate and correctly defined at the infinitely small scale. Google has used the Mercator projection because it helped in preserving angles of the road. So, preservation of angles means it's a conformal. So, Mercator projection is the application of the conformal mapping. So, you can see the mapping, this is the map of a road. So, the Google has used this Mercator projection for finding the path. The session was very clear about the conformal mapping. Thank you.